over. All right. Before I get going, any questions? So just a comment so you know I'm not slacking. I don't have a scanner here that's set up. So I don't scan the notes in. I'll post the video early, but I won't scan the notes until maybe this evening whenever I get home. So if you see them there, it's not that they won't be here. It's just it's taking me a while to get home and scan them, all right? But I'll do it this evening sometime. Does anybody have any questions about last lecture or the homework or anything else? So let me understand this. I did such a good job last time that nobody has questions. All right. So what we're going to talk about today is the square law equations, and then we're going to start developing an intuitive feel for how transistors operate. We're going to spend a lot of time on example 9.5. And in example 9.5, I love that problem, so you're going to need to know it backwards and forwards. There'll probably be quizzes and test questions on it and all that. So as I'm going through, which we won't get through it today, but as I'm going through, if you don't follow what I'm saying, you need to stop and ask me questions, all right? Or ask them next time when we start on Tuesday. Okay, so let's go, and I want to review the what we talked about last time, which is basic IV curves to start out with. Remember last time I gave you the analogy of using your house where you turn the hose bib on hose, and then you go out to the street and you turn the water on the street, and then you plot how the water flows. We're going to do that one again, but I'm going to do another one right now before we do that, and it's the following. You're at your house, and let's make sure we're recording. Yay. You know, one thing I keep wondering if I should do that would make it easier, you can take this, I think it's this thing, Evernote, and take pictures of the screen, and then I don't have to scan the note so that I take a picture every time and just save it. And I'll try that sometime. All right. It might be a little bit better quality. All right, so you're at your house in your normal operation, and you have a hose bib here. Right here. And you start and you ask yourself, okay, what I'm going to do is I'm going to plot the water that flows against the number of times I turn the valve on. Is everybody cool with that? And unless you've got a messed up valve, you don't just barely turn it and water comes out. You have to turn it a little bit before water comes out, right? So if I start to turn the valve, I'll get something like this, and then the water will start coming out, and the more I turn the valve on, the more the water will flow. Does everybody agree with that? Does everybody understand that? This point right here in the MOSFET is the threshold voltage. For an N channel, it's V threshold N. That's the value when the MOSFET starts to turn on and you get current to flow in it. So I'm going to do the same exact test, but I'm going to do it for a MOSFET. So for a MOSFET, we have the following. Okay, we need water pressure applied to the house. So that's going to be our VDS. That's our water pressure applied to the valve. Then I'm going to take VGS, and I'm going to sweep VGS from, say, 0 to 5 volts. Everybody cool with that? Okay, so if I do that, what's going to happen is I'm going to hit the threshold voltage and current's going to start to flow. So below the threshold voltage, it doesn't magically all of a sudden current starts flowing, but you can, if you go slow enough, you'll get a little bit of current flowing below. It's not a perfect valve like your hose bib is. The hose bib, you can shut it off and no water is going to come out, right? With the MOSFET, there'll still be a little current flowing down here. That's called the sub-threshold current. We'll talk about that later in the course. Your calculator and your watches, they operate with currents in the sub-threshold region. So those small currents, and that's how you're able to power the calculator with a solar battery or with a solar cell, is that they operate at very small currents below the sub-threshold region. Okay, so the key point here is not to get confused, other than to say their current here isn't zero. There's some current that flows called the sub-threshold current, and we'll talk about that. If I write the equation for this curve, it's the following. The drain current, which is the current that flows like this, from the drain to the source is equal to Kp, transconductance parameter of the N. So there's a Kp for the PMOS as well. Kp sub P divided by 2 times W over L times VGS minus V threshold N squared. And this is valid for VGS greater than the threshold voltage. What does that mean? Yeah, I'm getting some current flowing, right? For this equation, if VGS is less than the threshold voltage, I'm just going to say ID is 0, even though we know it really isn't. Okay? And it's also equal to, it's also valid, and we'll talk about this more later, for VDS greater than or equal to VGS minus V threshold N. In other words, it's in saturation. And I want you to explain this to you in simple terms. If I look at this and you think about it, if I have not too much water pressure from the street, from the water company, and I start to turn the valve on, eventually the water company's lack of pressure is going to influence how much water comes out the valve, right? So if I don't have much pressure at the street and I turn the valve on, I start to get water to flow, but then the low pressure in the street keeps the water from coming out and continuing to flow up like this. Same thing in a MOSFET. If I don't have a big enough VDS, I'm not going to have enough pressure across here to have current flowing where it continues to go up. If I have a small VDS here, it'll kind of flatten out, and the VDS will limit how much current that flows. Does everybody follow? That's when I go into the saturation region, or I'm sorry, the triode region. For this is the saturation region. Okay, we'll use these equations, but does everybody intuitively understand what's going on here? Why I have to have a big enough VDS? We're going to use this over and over again. For saturation, VDS has to be greater than VGS minus V threshold N. Makes sense. If the VGS is really large, but VDS isn't that big, it's not going to stay in saturation, and the water company is going to limit how much water flows. Is everybody cool with that? So this is for saturation. And just as a sanity check for myself, what would the corresponding equation be if I wanted to ensure the device was in triode? Well, I'm the king of trivial questions. Yeah, it'd be less than. I just flipped this to less than, right? And when it's equal, it's on the border of saturation and triode. Any questions? Mm-hmm. Yeah, so the question is it okay when you're determining threshold to tie the gate and drain together? Because, yeah, no, no, if you tie the gate and drain together, you do this and just apply a voltage. And then you look for when current starts to flow, and that's your threshold. And generally, it depends on the device. If it's a normal MOSFET, you might say, oh, when 1 microamp flows, it's on. If it's a power MOSFET, you say, oh, when 10 microamps flows, it's on. So it just depends how you pick. The key thing here in real life, if you go work in the industry, that isn't a precise value. Depends how you define it, right? Any questions? Yes? I'll get to those next. The lambdas and all that I'm going to cover right now. Any other questions? Okay, does everybody feel comfortable with this equation here? Okay, so let me just pause and let's do an example, and then let's do some simulations just to make sure it's clear. So here's the example. So calculate ID, and I'm going to use books, 1 micron process, and assume W over L is equal to 10. So maybe W is 10 and L is 1. And you say, oh boy. I go look in the back of the book, and I look at the 1 micron process, which is this one right here, and I see that I see that Kp is 120. I see that V threshold N is 0.8 volts. So I'm going to write those two down. V threshold N is 0.8. Kp is 120 microamps per volt. Does everybody see where I got that? So I get Kp sub N equals 120 microamps per volt, and V threshold N equals 0.8 volts. Yeah, volt squared, thank you. Right? And then I go, gee, you're not challenging me. It's 120 microamps per volt squared divided by 2. Let's make sure I'm using the right equation. Boom, there it is. It's in the front of the book too. With the lambda and all that stuff we'll cover in a moment. Times 10, which is W over L, times 1.8 minus 1. See how lazy I am? Or minus 0.8. I was getting ahead of myself there. So that's 1 squared. So that's 5 times that says 600 microamps. Any questions? Okay, so let's simulate that. And let's also simulate the IV curves, but let's do this one first. Questions? Okay, notice if I change this to W is 100 microns, L is 10 microns, or W is 10 microns, L is 1 micron, whatever, I still have a ratio of 10. So when I do the simulation, I have to pick sizes. So everybody going to remember 600 microamps, 1.8 volts? Okay, I got a question. What if I change this to 2 volts? What do you expect is going to happen? I'm increasing how much I turn the valve on. What do you think is going to happen? Yeah, you're going to get a bigger number. More current's going to flow. I'm turning the valve on. I'm asking the equivalent of if you turn the hose valve on more, is the water going to go up or down or stay the same? Well, it's going to go up. Increasing the VGS, turning the valve on, it's going to go up. Okay, so let's go do an example, or these two examples. What's that? Yeah, then you're not changing the position of the valve if you leave it at 1.8. Okay, so let me just show you something here. Let's go back to the book web page. And if you look, there's this file here called cmosmodels.txt. I don't know if it's on my desktop, but it said use the book's MOSFET models. There's 2 different processes that used in the book, the 1 micron process and the 50 nanometer process. One's called a long channel, the 1 micron, and the other's called the short channel. When we do projects in the class, we're not going to use the book's MOSFETs or process. We're going to use a real process from industry, okay? And we'll talk about that later. But for now, we're going to stick with the book. So I'm going to say save link as, and I don't have that on my desktop, so I'm going to hit save. Then I'm going to drag that over in here. Does everybody see that? The file name's actually cmosedu.models. Okay, of course you'll have this directory if you want to play around with it. So then I'm going to go here. You know what? That went away yesterday when I rebooted. Oh well. And then I'm going to go File, Save As, and then let's go Lecture 2, Example 1. And I'm going to zoom out. Let's get the scissors out and just cut everything. And because I always forget to do this, I'm going to do it first. I'm going to put a .op, which is a SPICE directive, and I'm going to say .include cmos_edu_models.txt. If I don't have this in my sim when I'm using transistor models, it's not going to know, it's going to use some other model. You're not going to know what it is, and then you're going to get frustrated because your hand calculations and your simulation results aren't matching. So everybody follow that. So you got to have that in there. So if you do, you're doing your sims, they don't match, make sure you check and see that you have this statement. Okay. Next thing I'm going to do is I'm going to add the MOSFET model. or the MOSFET component. In this class, we're going to use for the NMOS, NMOS 4, and for the PMOS, PMOS 4. So I'm going to click on that, and I'm going to plop that down. Now I'm going to right-click on this, and I'm going to set the length to 1U and 10U. Don't use, for just getting in a good habit, don't use 1 and 10, even though for this DC sim you'll get the same results, because that means 1 meter and 10 meters. And a MOSFET's not practical to have a length of 1 meter. Okay, you might be able to put a bunch in parallel and get 10 meters, but for what we're doing, we won't do any of that. So use microns. If we do AC, when you have a device that's 1 meter by 10 meters, the capacitances are gigantic and nothing works. So don't get in the habit of using meters. Okay. The other thing is, see this model name? The model name is actually N_1U. Now, it's a pain to do this every time, so that's why it's good to copy, okay, from one schematic to another, so you don't have to spend all the time drafting. Okay, so I'm going to do this, and I'm going to see this, width and length. I'm going to hit OK. Before I notice that L and W aren't seen on the symbol and I show you how to show them, I'm going to go back and double click on this and look and see, here's the MOSFET name for the 1 micron model. Here's the MOSFET name for the PMOS 1 micron. Go down. Here's the MOSFET name for the 50 nanometer. And here's the MOSFET name for the PMOS 50 nanometer. So if I go and I'm using the 50 nanometer process, I have to change the model name to N_50N. Okay, so now when I'm doing design, I want to make sure that I know what sizes of devices I have. Because if I don't, and I have a device that's sized wrong, things won't work out. So if I look at this, I can't see the size. So the way you show the size, you're going to want to remember this, even when you have like resistors and you have a series resistance or a capacitor with a series resistance, or you want to include other things, is you press Control and right click. Now you see this value, L equal 1U, W equal 10U. You double click there and then now it shows up. And knowing your sizes of your devices is important. Okay, now I can press G, or I can go up here and grab this. Then I can go up and grab my voltage source, which is right here. Plop that down. Press G again. Boom. Everybody happy with that? Okay, then I'm going to go over here and I'm going to plop the wires in here, and then I can either run a wire over or I can press G again and put a ground connection there. So in this class, the body or bulk, this terminal right here of our NMOS, will always be at ground. It will always be connected, and if you see it connected some other place, you're doing something wrong, or whoever connected it some other place is doing something wrong. What else do I need to do? No, the source can be at a voltage other than ground. The body is always at ground. This terminal here is always at ground. No, it can't be unless it's a discrete MOSFET or something, but in a real integrated circuit process, the NMOSs are in the P substrate, and the P substrate's always ground. That's the body. So we need to do 3 more things. What are they? Put a wire here. Yep. Put a voltage here of 1.8. What else? Tell what kind of analysis we want to run. Okay, so last time we did a .dc, and I'll do that again in a moment. This time I'm going to do a .op, just for operating point. And I could do it like this, or I could poke the running man and go to .operating point, and then OK, and it'll put it right there. And then it says ID is 422. Uh-oh, what did I do wrong? 422 micro, and the node is, and I calculated 600. But let's see what happens. If I put my cursor right here, it says 422 micro. Okay, does everybody see that? And I calculated 600, and I'm going, what the heck? How come my calculation's wrong? Any questions before I discuss that further? Let me just make sure I got the values right. Yep. All right. I know what the issue is. Any questions on that? Okay. Let me pause and discuss this, because one of the things in real life when you're doing real design is things don't get precisely the same values. And I want to explain why in this example. And then we'll come back and see if I'm right. In a real MOSFET, if you look at the cross-sectional view, hopefully you've seen this before. Has anybody not seen this cross-sectional view before? Has anybody seen it before? Okay. Okay. So this would be like the source, this would be the drain, this would be the gate. This is the body. This is why it's always at ground. When you use the minimum channel length, when you implant these N+, they actually go underneath and influence the behavior of the device. Okay, so it changes the effective L. So if you make the L longer, then you can get a more accurate results, because this influence or variation in L doesn't modulate or change the current. Does everybody follow that? And this is the lateral diffusion. Any questions? Okay, so but what bothers me after I say this is what happens to this is the length of the device here. What happens to the length of the device if I make it smaller? I mean, I include a lateral diffusion. Does the length get smaller or bigger or stay the same? If the lateral diffusion comes in here, what happens to this length? Shrinks. And if I look at the equation, it's W over L. What happens to this term? It should get bigger, right? So I'd expect the current to be larger. So I'm concerned. But let's see what happens if I make that less of a factor. How do I do that? What's that? How do I make the length, that variation in the length, be less of an issue? Just make the length really long, and then that variation doesn't influence things as much. So if I make the length really long, and I still need a ratio of 10, and I go back and I hit run, and it didn't go up that much. So you know what? I'm suspecting the threshold voltage isn't exactly 0.8 volts, because I don't know why it's not more precise. But let's go on to the next example and see. All right. So let's do that. Let's go open this again and say File, Save As, Example 2. And then let's change this to VDS. Whoops. And let's just put 2 volts. Just picking something there. That's my water pressure. Now what do I need to do? I need to turn the valve on. So I'm going to go grab, copy this, and do a Control E. Rename this to VGS. And then I'm going to sweep VGS. So I could poke the running man, but I'm going to do it manually because I like doing it that way better. .DC, sweep VGS from 0 to 2 volts in 1 millivolt steps. Get out the scissors, cut this. Anybody not follow what I just did? Anybody follow what I did? Yeah. So VDS is like the pressure from the street. I put it up at 2 volts, so I'm applying pressure from the street to the house. Then now, what I'm going to do with this is I'm going to turn the valve on and go from 0 to VGS in 1 millivolt steps. So now I'm turning this on, and I'm going to plot the current that flows in the MOSFET. Yeah, it's just a battery. I just put it at 2 volts, yeah. So I don't have to do anything with that one. In the next sim I do, we're going to sweep both of them at the same time, which is more complicated, right? So we're going to have 2 loops. Questions? Anybody not follow how to do this? So if I give you a quiz on Tuesday that says sketch the schematic for how you would simulate the IV curves, ID versus VGS of a MOSFET using LTspice, everybody would get it right, and you would say this didn't challenge me. Okay, so let's poke the running man there, plot the current, and so it says 0.8, but it's closer to 0.9 in the sim. That's where we start to see appreciable current. But if I put a like 0.9 in, what do you think is going to happen to the ID? It's going to get closer to what I calculated. Does everybody agree with that? Okay, so you see, there's no magic here. It's not like I'm doing real life engineering. It's not like everything's just, math. So you expect things not to be precise in real life. Does everybody see this? And refresh my memory, how do I save this auto plot so that when you open it at home tonight and look at the sim, click this and then hit save. And then now, when I go back and I hit run, it automatically plots. So if the question is if you change it to 0.8 to modify, but here, let me show you what's in the models. The threshold voltage is set right here at 0.8, but there's other things that come into play with these other parameters that try to model real life MOSFETs that adjust the threshold voltage, so it changes a little bit. The key point here is if you see something and it's not exactly what you calculated by hand, you should expect that, because it's only going to be exactly what you calculate by hand is if you use the exact same parameters. And if you have other things and it's real modeling imperfections in the devices, it's not going to be precise. And that's a really big, tough thing for the students to get over when they're learning real engineering. Okay? All right, so let's go and go back. And I'm going to do a PMOS real quick before we leave this. Now the PMOS is a little bit more complicated because it has it's a complementary device. So instead of the source being connected to ground, we generally will connect the PMOS's source to VDD. And it gets a little confusing. So here's the PMOS, and unless we say otherwise, as a side note, I don't know what MOSFET symbols you're used to looking at, but what we'll use in this class is the following for drain, gate, source, and then if we have the bulk. But there's other symbols like this. Or for an N channel, you might actually see, and there would be the body there if you wanted, you might actually see an arrow going the opposite way where this represents the N type, like a diode, the N channel, and then the P substrate. We're not going to use this one, and we won't use the arrow, the bipolar drive symbol. We're going to use this one. But all these would be drain, gate, source, drain, gate, source. Okay, for the PMOS, you might have been using this one. We're not going to use that. We're going to simply use this, and it'll all be source, drain, gate. Notice it's complementary. So in the NMOS, we had the drain at the top. In the PMOS, we have the source at the top, and the drain is at the bottom. And here's the gate. For controlling the current in the device in the NMOS, we talked about what? What controlled the current in the NMOS? VGS, right? Everybody cool with that? You're not thinking deep here. You're thinking, how many times I turn the valve on, that controls the current, VGS. Here, for the PMOS, we're going to talk about VSG. because it's complementary. That's the whole C in CMOS. For the NMOS, the pressure from the street was VDS. Here the pressure is going to be VSD. Okay, so just as a sanity check for myself, what do you think I call the voltage at that node? V source, it might be tied to VDD. This node is V drain, and this node is V gate. So VSD equals V source minus V drain. VSG equals V source minus V gate. Yay or nay? Okay, so what's going to be different here is that when I go to, so I'm going to connect my source to ground, and then I'm going to apply a pressure to the drain. Whoops, sorry. That should have been very confusing to you. And I'm going to call that pressure V source to drain. What is the drain voltage in this schematic? 0. It's grounded. Now, here's the issue. You're going to tell me what's going to happen. Here's my source to gate voltage. If I ground that device, what do you think is going to happen? Look at the pressure between source and gate. Do I have pressure there? What's the, when I say pressure, voltage? Do I have voltage between the source and the gate? Yeah, so do you think that device is going to be conducting? Yeah, so when I drive the gate down away from the source, it turns the device on. Well, gee, of course it does. It's complementary. When I drive the gate up in the NMOS, it turns the device on. So here I drive the gate down and it turns the device on. Is everybody cool with that? So how do I shut the device off? How do I get zero current to flow? Yeah, if I want zero current, I can connect the gate here, and then VSG goes to 0, and the device shuts off. What's the gate voltage when I do that? Whatever this voltage is here. Everybody follow that. So I drive this voltage up, shuts the device off. That's what the little bubble means. It means it turns on when the voltage goes down, it shuts off when the voltage goes up. So let's do another example. If I do the following. Or whoops, V gate, sorry. Which way does the drain current flow? Flows like this. That's one thing. Current always flows from the top of a schematic to the bottom. For the PMOS, it flows from source to drain. For the NMOS, it flows from drain to source. So the current doesn't flow one direction and the other unless you look at what's coming out of the drain in the PMOS and going into the drain in the NMOS. But for the schematics, current always flows down. Input should always be on the left. Output should always be on the right. Now, that doesn't mean you're going to see some crazy engineer draw schematics where the current's wiggling all over the place, right? But in general, you want to keep the schematics so that they look nice and are easy to follow. So I want to plot here ID, I'm going to do this two ways, versus VSG. And then we're going to do it versus V source, or V gate rather. So tell me, when is VSG 0? When is VSG 0? What is the gate voltage? 2. Everybody follow that? If it's 2 volts, then I have 0 volts here. VSG is 0, how much current flows? None. When I move this up to 2 volts, the MOSFET shuts off, VSG is 0. So I'm right here. As I start to drop the gate voltage, as I start to go from 2 down to 0, what happens to my V source to gate? If this is 2 and I go from 2 to 0, it's going to go up and give me this curve. It's exactly the same as the NMOS. It's a transistor curve. It's a valve. It turns on. This is called the threshold voltage, V threshold P. And for the PMOS in this, it's 0.9 volts. If you look at the back of the book. Is everybody cool with that? Okay, so now I want to do the exact same plot, but I want to use V gate. The asymptote. Yeah, so right here would be 2 volts. Yep. Okay, but let's plot V gate now. If V gate is 0, well, what's the status of this device? It's on, right? So I get a current flowing. And then as I drop V gate, as I increase V gate towards 2 volts, towards this here, what happens? It's going to go down like this, and this will be 1.1 volts, 2 minus 0.9. So as I drive this from 0 to 2 volts, the switch starts to shut off. And I'm going to do this in a sim. Any questions? So let's go back. And because I'm lazy, I'm going to take this and do File, Save As, and I'm going to save it as example 3. And then I'm going to get the scissors out. And I'm going to plop down a PMOS IV. And for some reason, when he puts the symbol in, it doesn't really matter. Source and drain are interchangeable. But the way the netlist defines source and drain, it's the drain in here is on the top and the source is on the bottom. But for us, it doesn't matter because source and drain are interchangeable. So all I'm going to do is I'm going to do a Control E, then a Control R twice, so that the source is at the top. And you probably don't understand what I just said, so let me make sure. So if I go to View, Spice Netlist, this is my device right here, M1. This is the drain gate source bulk. Okay, and I want the drain here to be on the bottom. That's why I flipped the symbol. Again, it doesn't matter for what we do because source and drain are interchangeable. For now, everything we do in this class for now, we'll change it later. And if you read in chapter 9, it probably talks a little bit about body effect. The source and the bulk will be tied together. Okay? So, I'm going to change this value. What do I change this to? Yeah, VSD. And then I'm going to move this up. I'm going to come over here and I'm going to change this to VSG. And again, when I do a DC sweep, this voltage doesn't matter because it's sweeping it from 0 to 2. Questions? So when I first start out and I look, I have to do two more things here. I have to change the name of the model to 1U, and then let's put the width and the length 1U, 10U. And then how do I show those on the symbol? Control right click. There they are. But of course now you can copy. Oh, this is something. Let me just pause for a sec. Hit save. How do I copy from one schematic to another? I open the schematic. Let's say we open this one. I go grab the copy what I want, then go over here to the other schematic, and there it is. Okay, you have both schematics open. Control C and copying to the clipboard doesn't work. Did everybody get that? Okay, so I click here, close this one, go back. Now I'm ready to sim. What do you think I'm going to see when I plot? Which schematic? I'm going from 0 to 2. When we start at 0, are we going to have a lot of current or not much current? Oh yeah, I need to sweep this. And I could have changed it right there too. So what was that? Yeah, it's going to be a lot of current. And as I go to 2 volts, these two are equal. What's going to happen? It's going to shut off. So I'm going to hit run, plot the current that flows. There it is. Boom. Hey, I know what I'm doing. This should be 1.1. Hey, it is. Why is it 1.1? Because it shuts off when this voltage gets within a threshold voltage of this one. Looking good? But hey, I don't like that plot. I want to plot ID versus VSG. So here's what I'm going to do. I'm going to save this. Then I'm going to close this. And come back over here. Do File, Save As. And go to example 4. And then I don't have to do anything in a sim, right? I could do it. I'm going to do this 2 different ways just to show you. So I hit run, plot the current. Then I come down here and I right click on the axis, or left click on the axis, and I plot VSG. I want to plot this voltage minus this one. So how do I do that? Well, I can name this node or whatever. I'm going to be lazy, and I'm going to click there and just go quantity plotted 2 minus. Why is that? This is 2 volts minus this voltage is VSG. So I hit OK. Hey, I know what I'm doing. There it starts to turn on, 0.9 volts and goes up. I'm going to hit save on this. I'm going to do one more sim. But before I do, are there any questions? So I'm going to come back here. And I'm going to do a file, save as. Did I save the plot on that last one? Let's double check. Yes, I did. You can tell because there it is. I want to plot VSG versus without playing with any games. So here's what I'm going to do, and you tell me if it's all right. And you know what? I should be more correct. And let me fix those because I labeled that VSG, and it's not VSG, it's VS. So let me go back and fix those. What's that? Yeah, it's VG, sorry, yeah. Keep getting past performance. You make a mistake, you're going to keep making mistakes. All right, so I'm going to hit run. Does everybody see what I did? Well, is it okay to do this? When VSG starts at 0, what's this voltage right here? When VSG is 0, what is a 0 volt voltage source? A wire. So if I have a wire connecting these two together, what's the voltage here? Same as the voltage here, 2 volts. Does everybody agree with that? But as VSG starts to get bigger, say VSG is 1 volt, I get a power down. 1 volt, I go from a high potential of 2, drop 1 volt, and this becomes 1 volt. When this becomes 2, I go from 2, power down, to 0, because I drop down in potential. This is going downhill. I don't think deep when I see this. I say, hey, I'm at a high potential here. I'm on the hill. I see this plus to minus. I'm going to go down the hill and drop that much in voltage. So if this is at 1.5 and this is at 2, I go down the hill and this is at 0.5. Is everybody cool with that? So then I hit run, plot the current. Boom, now I'm plotting ID, or IS since they're the same, versus VSG. Questions? Yes? When I change this, you mean in this one or in the previous? No, I just look. This is all this means is I subtract whatever voltage is here. I subtract 2 volts or whatever the voltage is, and that's the voltage here. And if I'm going here and I know the voltage here, and I see this voltage source, I add. So this is like I'm going uphill, and when I go from plus to minus, I'm going downhill. So if this was at 1, and this wasn't connected, and this was 0.5, then I'd go, this is 1.5. Okay, let me go do the other ones where I use a different source here. So, did that answer your question or not? Yeah. Yeah, if I flip this around, and this was at 2 volts, and this is 2 volts flipped, then this would be a power up, this would go to 4. Yeah. So let me go fix those other schematics real quick. That one's okay. That one should be V-gate. Okay, and that means I have to fix this. V-gate. Save. Run. Oh, knew what to plot. All right, so that one's fine. Any questions? And then the last one was this one. That should be V-gate. Save. And run. Oh yeah, thank you. Keep me honest, man. And run. Ooh, what am I plotting there? How do I fix it? Yeah, boom. Now, we're going to go through the IV curves of the MOSFETs for the case where we have the valve on in the house and then we're turning the water on in the street. The whole point today is I want you to understand the equations in the MOSFETs and not operation and not just see math, all right? I want you to understand, hey, if the gate goes up in this NMOS, the device turns on. If it goes down, the device turns off. The PMOS, the gate goes up, the device shuts off. Gate goes down, device turns on. I don't want you looking at the circuits and going, oh, where's the math? Where do I get my algebra here? I want you to understand and feel what's happening so that you know how to adjust things, okay? Okay, so let's close this. Go back. And do the following. I'm going to do the house example. Here I've turned my valve on. If I only turn it half a turn, what's the problem? Might not be turned on enough to get any water flowing through it. So then I go out to the street or in front of your house and I turn the valve on there. And then I plot the water that flows for street valve turning on. And what happens? As soon as I start turning the street valve on, I get a little bit of pressure, a little bit of water flowing. I get a curve that looks like this until this valve starts to limit, and then the current or water saturates and flattens out. I go to 3 turns. What happens? This one I turn to 3 turns. Yep. Questions? Is it making sense? Okay, so now I'm going to do the same thing for the MOSFETs now. Whoops. And I plot the curve. Pressure VGS always 2 volts. I start to increase this potential from 0 to 2, what happens in the curve? I get this curve right here, right? I start increasing this potential, I get a little bit of current that flows, because in this region, what does the MOSFET behave like? A resistor. I change this to 3 volts, and what happens? Now note, I'm only changing one thing at a time. When I sweep this, I'm not doing the same. I'm not changing this a little, then changing this, and changing this a little, and changing this. Okay, I get this curve. Okay, so wait, what about the PMOS? So in this case, I'm assuming the body's tied there. For the PMOS, VSD is swept. This was VDS. This was VGS, VGS, VSD. Now I'm going to put, because I don't like messing with that reference down, I like looking at it like this. I'm going to make this VSG. And I'm going to set that to 2 volts. And I'm going to sweep VSD, and what do I get? Same curve. Change this to 3 volts. Sweep VSD, what do I get? Same curve. Now, you might argue, well, wait, if you go to 3 volts and this is 2 volts, is it going to work? Let's find out. VDS greater than or equal to VGS minus V threshold N. If this is 2 and this is 3 and this is 0.8 or 0.9, you can see that, well, I'm lying a little bit, because over in this area here, the valve starts to limit and the current will start to drop a little. I can simulate that and look at it, but I understand what's going on. I just simply need to increase how far I sweep this. Okay, and I'm not thinking in terms of anything deeper other than me standing in my yard and turning valves on and looking at the water that flows. Okay, now, any questions on these two curves or these two circuits? I'm going to do a sim in a moment, but I want to write the equations first. Is it making sense? Is the pain factor high? No pain, no brain. Yeah, for the PMOS, it's the same exact thing. VSD greater than or equal to VSG minus V threshold P. Note, when you took microelectronics, they may have talked about negative voltages for like VGS or whatever. For PMOS, we're not doing that. We're always going to talk about positive voltages. That's why we use VSG. We also, when we say VSG, you don't have to ask me, are you talking about a PMOS or an NMOS? Because you know it's a PMOS. And if I say VSD, it's a PMOS. If I say VDS, it's an NMOS. Right? So I don't have to think about it. Any questions on this? Yeah, so if I look and I only have a 2 volts there, and I'm only sweeping up the 2 volts, well, I'm really never getting out of the region. If I were to draw this curve, I'm never really getting out of the region where the valve starts to saturate, because I've got the valve on so hard here, 3 turns, that the pressure out here doesn't go high enough for it to saturate. Yeah, yeah. Any other questions? So I want to go over the equation for the curves in the saturation, not this part. And that's a little confusing, because remember in the previous plot, I'll go over these. There'll be 2 sets of equations. There'll be one for the triode and one for the saturation. Okay? And we're going to do it fairly quick. And for the saturation, we have ID equals Kp times W over L divided by 2 times VGS minus V threshold N squared. And you say, wait, that's exactly the same equation as I had for saturation in the other case. Yes, it is. Now, later we're going to go over the following. We're going to have, remember, if the MOSFET curves aren't perfectly flat in saturation, they have like a resistance. The way we're going to model that in the equation is we're going to add this term here. Okay, let me just tell you, we won't use this. other than deriving some equations. We will base it to model the output resistance. When we do our hand calculations, we're not going to include this because it gets to be too algebraic and doesn't give us really that much added accuracy. So we're just going to use this part. Is everybody cool with that? So this is for, what's that? Yeah. We're not going to use hand calculations with this. Now, the exception to this is when I derive the output resistance of the MOSFET. When I derive the output resistance, this little variation in how the curve, that is the output resistance. I got to include it. But it doesn't make sense to include it in all the other DC calculations, so we won't. Burn that in your brain because you'll minimize your pain. Okay? This is for VGS greater than what? Threshold. Hey, man, no current's going to flow if you don't turn that valve on above the threshold. And it's for VDS greater than or equal to VGS minus V threshold N. You got to have enough pressure for the current through the valve, through the MOSFET to saturate. Questions? For the other area, the triode region in that plot, its ID is equal to Kp times W over L. Notice there's no 2 times VGS minus V threshold N times VDS squared over 2. What? Telling me no, man? Whoops, no, there's no 2. Yes, thank you. Minus VDS squared over 2. Oh, yeah, you're right. Thank you. I was getting too focused on this term right here. I wrote it first. Does everybody see that? That's for VGS what? Yeah, this one you don't think deep on. The valve has to be turned on in order for current to flow. Is everybody cool with that? And then you think, oh, well, if I'm not greater than, it's less than, right? It's the other way. And then when they're equal, and you plug in VGS minus V threshold N for VDS, the equations are the same. Yay or nay? How do I write the equations for the PMOS? Yeah, VSG, V threshold P, VSD. Or VSG, V threshold P, VSD. Does it make sense? Okay, so let's do a sim. These are in the front of the book in case you can't read my handwriting. So here's the equation for the triode region. VDS minus VDS squared. And then there's the equation for the saturation, and there's the lambda term. Oh, okay. All right. Any questions? So we're going to sim, then we'll have our little grade booster, and then we'll have a good weekend, right? Okay, so let's go. Let's just pick one of these. How about we pick this one? Killing me. I don't know what this means. Okay, so I'm going to go File, Save As, and call this Lecture 2, Example 6. And what do I need to do here? Not much. I just basically need to redo this equation. I'm going to change it so that VDS is swept from 0. Hey, let's just go to 5. And then VGS is swept from 0 to 5 in 1 volt steps. And this is where you could mess up and have a lot of data. Because VGS is my valve. I'm going to do it 0 turns, 1 turn, 2 turns, 3 turns. I'm not going to do it 1 millivolt, 2 millivolts, because then I'm taking a lot of data, right? But here, my VDS, that's the valve on the street. I'm going to continuously change that from 0 to 5 volts. So my VGS, the valve at the house, I'm going to set it in a position. Then I'm going to sweep the valve on the street. Then I'm going to go back and turn the valve off on the street, set it in a position at my house, 2 turns, sweep the valve on the street, etc. Does everybody follow that? Okay, so I hit OK. Then I'm going to hit run. And now I'm plotting these curves. So now, just as a sanity check for myself, what am I plotting right here? VDS, that's sweeping this voltage from 0 to 5. Note the 2 is ignored because it's being swept. What is this if I zoom in here? What is the green? How many turns on the valve? 0. What is the blue? 1 turn or 1 volt, and that's just a teeny bit above the threshold voltage. If I look at the red, what is that? 2 volts, 3 volts, 4 volts, 5 volts. Any questions? Do these curves make sense to you? Okay, so I'll go back now. I'm going to do the same thing for the PMOS. Before I do, any questions? I got a question. What if I change this to, oops, before I do that, let me make sure I save this so it automatically plots for you. What if I change this to 1? What do you think is going to happen based upon the equations? ID equals W over L. If I make L smaller, what happens to ID? Goes up. So I look at this and I go, okay, it's going to 6 milli. I run the sim. Now it's going up even higher. Okay, let's put it back to what we had. Whoops. And hit run. Okay, any questions? Let's do it for the PMOS, and then we'll stop and do our grade booster. How do I do here? VSD from 0 to 5 volts. And then I'm going to make VSG go from 0 to 5 in 1 volt steps. Any questions? Yes? No. VSG starts out at 0 and it's a wire. So no current will flow, or very little. Then VSG goes to 1 volt and then I sweep the VSD. Then VSG goes to 2 volts and then I sweep this. Here's what I'm doing. This is me standing in my yard with the valve. I leave the valve off, 0 turns. I go out to the street and I turn the valve in the street and I plot how much current flows in the hose bib. None. Turn the valve on my house, 1 turn. I go out to the street, turn the valve water on again, I plot. Then I put it at 2 turns. Go out to the street, turn, and I plot it. Okay, so when I hit run, I go up and I get these curves. You know what I did? Forgot to save it as 7. So let's close this. Let me make sure I didn't mess up this sim. Okay, I didn't. Still good. Then let me go back here. Hit run. Let's plot current going out here. All right, let's plot it here so it's going in. Oh yeah, that's a good point. If I plot the current here, what am I going to get? No, the current flowing in the source is equal to the current flowing out the drain, right? But SPICE defines positive current flow as current flowing into the device, and negative current flow is current flowing out of the device. If you have a resistor and you plot the current on one side of the resistor, it's going to be going in. That'll be positive. If you plot it on the other side, it'll be negative. So if I plot it here, there it's negative because it's going out. Does that confuse me? No. I just put a minus sign in, or I go over here and I plot the drain current as what here we call the source. It says I source. Source and drain are the same currents. It's a pipe. What comes in one side of the pipe has to come out the other. But I'm not confused by that. So what SPICE defines as positive and negative. So then I hit save. What is the valve turn right here? 5, then 4, then 3. But if I ask, okay, if I'm at a VDS or a VSD of 3 volts right here, and VSG is 5, so this voltage is 3, this voltage is 5. What is this voltage here? -2. right? You go from 3, you drop down 5 volts, and this is minus 2. Okay, if you don't believe me, save this. It's easy to hit save as. Save it as lecture 2 example 7. Go to .op, change this to 3.5 or wherever I was. Change this to 5, and then just see what the voltages are. All right, any last second questions? All right, we shall stop then.